All right, so I'm going to start with this is a first video in showing how corollary 3.12 of IUT3 implies theorem 1.10 of IUT4, or something like this. Okay, and so this is about log volume computations. So this is part 1. So this is joint work with graduate student Anton Halato. Okay, so I guess I'm just going to start. First, let me say a couple things about difference first. So to kind of to understand what this is. So, well, okay. So let me just give the statement. Okay, so for so the lemma says the following. So this is the first upper bound. Okay, and what it has to do is it has to do with the local part of the multi-radial representation of the theta pilot object. So this is this region U theta from the corollary 3.12 video. So okay, so let's let K1 through Km over Qp. So these are finite extensions. Okay, we're going to let A be an element of Km with absolute value of A less than 1. So the p-adic absolute value of A less than 1. Okay, and we're also going to take L. So this is going to be the tensor product of the ki's. I is equal to 1 up to m, which by the Chinese remainder theorem, right, is isomorphic to a direct sum. I is equal to 1 up to r, or so j is equal to 1 up to r of lj. And then O of L is going to be the direct sum of these fields. So if you have a product, so this thing's a product of fields, or a direct sum of fields. And this thing's also a product or direct sum of things. They're the same because there's finitely many. All right. So, okay, so this is going to be these things. Okay, and so the statement is about the okay, so what we're going to say is that this so-called holomorphic hole, which is the smallest polydisk containing the region I'm going to write down, into of this thing applied to OL and then ind 3 of A. So this is the third indeterminacy. So this is what the multiradial region looks like, is less than or equal to DL0R. So this is a polydisk with an explicit radius, R. Okay, so the thing is that we want to describe what this is. Okay, what this radius is. These guys here. So these are contained in this group. Log. Okay, I cross. So these are QP vector space automorphisms that fix this lattice pointwise. So essentially you can think of ZP automorphisms of the lattice extended to the L here. So this is a lattice inside here. You can count the dimensions. Okay, and then so then here, so this is defined via the indeterminacy diagram. Okay, so we have this thing. So for some explicit L, some explicit R, the radius R. All right, so we're going to have a bound of this form, and now I'm going to go and write down what this R is. Okay, so to define what the R is, right? So I need to set up some notation. Okay, so for some notation. So for K a field, so so a p-adic field, right? So we're going to define the different k over qp. So this is the order of the different exponent. Or sorry, I mean, it's kind of the different exponent, right? But here's the different, and we can take the valuation of this. And so I just want you to note here that there's some relation here. So diff k over qp. So this is an ideal, right? And so it can be written as pi k to some exponent here, d k over qp. So Machizuki doesn't work with these guys here. So these exponents will have different behavior. Okay, and then and so ord p of this different k over qp. So this is an integer, this little one. So this is this different exponent divided by the ramification degree. Okay, so there's a relationship between these things. This number here isn't exactly this exponent that appears, but it's related to it by division by p. Okay, so all right, so we have this, and then in our case, so we let here this number here. So this is going to be the vector of difference here. Okay, and so this is just a rational number, q to the m. Okay, and then what else are we going to have? So I think that's all I need. All right, and looks pretty good. Okay, so so we're just going to need this. Okay, so then back to our expression here. We want to describe this radius that bounds this, and so this is the polydisk in L. So this is our region L. L is this tensor product of these fields. Okay, so we're looking at kind of a factor of the overall multi-radial representation of the theta pilot. Okay, and so R, it turns out, so natural log of R. So this is equal to, so this is the upper bound, right? So this is the floor, and then we're going to take the order P of A plus, okay, so we take this different, we're going to take the maximum one, and then we subtract the minimum ones, all right? And then we're going to add M ln CP plus the sum of ln EKI over QP, like so. So I is equal to 1 up to M. Okay, so this is the number of, M was the number of fields that we had. These are the ramification indices here. This is going to be a constant coming from the upper bounds on the logarithms. And I guess this can be improved a little bit the way that I'm stating it right now, because when E is less than P minus 1, you get a different bound. And then that looks pretty good. Perhaps. All right, so let me write down the bound that we obtained from the previous video. Right, so we obtained that here that the whole of U. So we're going to say U is local here. So U here was so this will be a local factor of the whole of the multi-radial representation of the theta pilot object. So we have this, we take OL in 3A like so. Okay, and here L is a tensor product of p-adic fields. A is in Km. And then we won't say anything about the absolute value of A, the size of A. And so these are p-adic fields here. Okay, and then what we proved is that this was in, this is contained, this was contained in the disk for L, the polydisk for L, of radius R, right? And so what is R here? So R, so this was the result. So R here is given by, so it's P to the minus ord P of A minus ord P of beta. So this is this different term, and then we have so then we'll have that this is 2p over, so we'll have x1 natural log of p. This is all raised to the mth power, and then we have the product from I is equal to 0 up to m, or let's say I is equal to 1 up to m of ei, like so. So this was so this is our radius here. EIs are the ramification degrees here. X is the exponential. This is like 2.7182882, whatever. And then okay, and then so let me just say in the application. So this will be so m. So we'll actually start at index 0 here in the application, but this will be like q double underline v here j to the j squared. This thing will be so this gives a different term, so related to the different. Okay, and then this is what it is, and then those are the ramification indices. Okay, so or this is 1. Okay. I guess one thing we should observe is that in our application, the other thing that could happen is that most of the time this thing will be 0, actually. So, and then we actually don't need to consider this term. So we don't need this term most of the time. Okay, in particular, if when let's say the all the ki's are unramified, then R is equal to 1. Okay. In particular, when this is unramified, let me just say a little bit more about this. So this part here, comes from bounds on log shells. We can call it IL, and then in the case that if K over QP is unramified. So then IK, so this is 1 over 2p log OK cross. So this thing is just, so it's unramified, so this will be like 1/2 OK. So you have 1 over 2p 1 over 2p p OK, and then the 1/2 does nothing, it's just a unit, so this will just be OK. So nothing, so then to find an upper bound, right, to find the disk that it's in, the disk will be a radius 1, so nothing happens here. Okay. So Okay, also when it's unramified, so there's also this relationship between in this thing. So when it's unramified, you'll never have tape parameters, and then the different also doesn't appear. So none of these terms appear in the unramified case.